Deep in the cosmic dark, the universe hides its most extreme objects. We are going on a journey to the edge of everything we can see to uncover 50 incredible facts about the most distant neutron stars ever found. These are the universe's ultimate cosmic zombies, the collapsed cores of dead stars, and they hold secrets about mind-bending physics and the raw power of creation itself. By the end, you will understand how these distant relics are rewriting the rules of reality. We will explore how a single teaspoon of one weighs billions of tons and how their collisions forge the gold in your jewelry. What cosmic mystery are you most excited to unravel? A neutron star is the universe's ultimate leftover, the collapsed core of a giant star that exploded in a supernova. This is not just a simple ball of ash. It is a cosmic object so bizarre it defies everyday logic. Picture the entire mass of our sun, a colossal sphere over 1 million times the size of Earth, crushed into a city. That is the scale of a neutron star, an object typically only about 12 miles across. The gravity on such an object is almost beyond comprehension. It is so ferociously strong that it overwhelms the very structure of atoms themselves. Inside the star, the immense pressure forces protons and electrons to merge, creating a sea of neutrons. This means the entire star is in essence one gigantic atomic nucleus. The density this creates is what truly stretches the mind. To grasp it, think about a single sugar cube. If you could somehow fill that tiny cube with material from a neutron star, it would weigh over 1 billion tons. That is more than the combined weight of every single person on Earth. This incomprehensible density is the first clue to the extreme nature of these distant cosmic zombies, setting the stage for even stranger truths to come. But with such an unimaginably small size, how could we ever hope to find one of these cosmic specks across the vast emptiness of space? We almost never see a distant neutron star directly, as a tiny point of light in a telescope. Instead, we detect them by their energetic tantrums, their frantic screams into the void. The primary method for spotting these distant objects relies on their pulsing behavior, but only if they are a specific type called a pulsar. Think of a pulsar as a rapidly spinning neutron star, a celestial lighthouse. As it rotates, beams of radiation shoot out from its magnetic poles. If one of those beams happens to sweep across Earth, our telescopes register it as a perfectly timed pulse, a blink that can be more precise than an atomic clock. For neutron stars that are not oriented to flash at us, we have other tools. Many reveal themselves through intense X-rays or gamma rays, the most energetic forms of light in the universe. This often happens when a neutron star is not alone. In a binary system, it can orbit a companion star, a stellar partner. Its immense gravity can then rip gas directly from that star. This stolen material spirals down onto the neutron star's surface, heating to millions of degrees and erupting in a storm of high-energy radiation before it even arrives. To catch these faint, high-energy whispers from the edge of the observable universe, we rely on a special class of observatory. Space telescopes like Chandra, Fermi, and Neutron act as our long-distance ears and eyes. Positioned above our atmosphere, which blocks X-rays and gamma rays, they patiently scan the heavens. They are not looking for visible starlight. They are listening for the violent, high-energy signatures of accretion and decay, the unmistakable fingerprints of a cosmic zombie feeding. These instruments transform raw data into a map of the most violent and energetic neighborhoods in the cosmos, allowing us to pinpoint the location of a city-sized object from billions of light years away. That faint, high-energy whisper we detect from the edge of everything has a name and a home. One of the most distant neutron stars we have ever observed lies in a galaxy known as GNZ 11. The light from this object reached us carrying a phenomenal redshift. Redshift is a fundamental clue written into the light of every distant object, a cosmic fingerprint of immense distance and age. As the universe expands, it stretches the very fabric of space itself. Light traveling across this expanding space gets stretched along with it, much like a drawing on a rubber band that you pull apart. The farther the light has to travel, the more it stretches. This stretching shifts the light's color towards the red end of the spectrum. A high redshift tells us an object is not just far away in space, but also far away in time. When we observe the neutron star in GNZ 11, we are not seeing it as it is today. We are witnessing a cataclysmic event that happened over 13 billion years ago, when the universe was a mere infant, only a few 100 million years old. This makes the object a direct relic from the cosmic dawn, a time when the first stars and galaxies were just beginning to ignite. To look at this neutron star is to peer back through almost the entire history of existence, observing the aftermath of one of the universe's earliest stellar deaths. This distance makes them perfect time capsules. When we observe a neutron star from the cosmic dawn, we are not just looking at an object, we are looking at a moment frozen in time, a snapshot of the universe's chaotic youth. The properties we can measure from that faint signal are direct messages from that ancient era. For instance, the spin rate of a pulsar, that steady cosmic heartbeat, can tell us about the magnetic environment it was born into. The composition of material we detect accreting onto it holds clues about the chemistry of the very first generations of stars. Each of these measurements is a vital data point. They help us understand how quickly the first massive stars lived and died, seeding the cosmos with the heavy elements necessary for planets and life. They reveal the frequency of those titanic supernova explosions that churned the early galaxies. Every distant neutron star we find is another piece of the puzzle, helping us answer fundamental questions. How quickly did the first stars form after the Big Bang? Was star formation a frantic burst or a slow simmer? These cosmic zombies are not just relics, they are active informants, whispering secrets about the universe's first chapters. Their very existence helps us map the timeline of cosmic evolution, tracing the journey from a dark, simple universe to the complex, star-filled one we see today. This density is so extreme it warps our understanding of matter itself. We can talk about 1 billion tons in a teaspoon, but what does that actually mean for the material inside? The gravity on a neutron star is so powerful it crushes atoms into oblivion. The electrons, which normally orbit a vast distance from the atomic nucleus, are literally forced into the protons. This fusion creates a new, almost pure substance, a quantum sea of neutrons packed shoulder to shoulder with virtually no empty space. This substance is not a solid, nor is it a liquid in any normal sense. It behaves as a superfluid, a state of matter with zero viscosity, meaning it can flow without any friction at all. But the story of what lies deeper inside gets even stranger. As we move toward the core, the pressure becomes so unimaginable that even this neutron sea is forced into new, bizarre configurations. Physicists call this state nuclear pasta. Here, the immense forces squeeze the nuclear material into shapes that defy their own nature. It can form long, thin tubes that resemble spaghetti or flatten into wide sheets like lasagna. These are not just metaphors, they are the actual, predicted phases of matter under pressures that cannot be recreated anywhere on Earth. This cosmic lasagna is thought to be the strongest material in the entire universe, a lattice so dense and tightly bound that its crust can support mountains, albeit microscopic ones only inches high, which still weigh more than entire terrestrial mountain ranges. The very substance of a neutron star is a laboratory for physics that pushes at the edge of all known laws. This nuclear lasagna exists under the dominion of an invisible force of almost mythical power. While all neutron stars possess ferociously strong magnetic fields, a special class takes this to an apocalyptic extreme. These are the magnetars, the true magnetic monsters of the cosmos. To grasp their power, first consider the gentle magnetic field of our own planet, the force that guides a simple compass needle. A magnetar's field is up to 1 quadrillion times stronger. This is a number so vast it loses all meaning, so let us frame it with a startling consequence. If a magnetar were located as far away as the Moon, its magnetic field would still be powerful enough to erase every credit card on Earth. The source of this unimaginable force lies in the star's violent birth. As the massive star's core collapses to form a neutron star, it spins faster and faster, much like a figure skater pulling in their arms. This spinning, combined with the frantic churning of superheated, electrically conductive fluid in its interior, acts as a colossal dynamo. It amplifies a regular stellar magnetic field into something truly monstrous in a fraction of a second. This magnetic prison holds the star in an unbelievably tense grip, storing catastrophic amounts of energy. The crust of the neutron star, that incredibly strong nuclear posture, is not immune to this stress. It occasionally cracks under the strain. These are starquakes, seismic events on a scale we cannot fathom. When the crust fractures, it releases more energy in a fraction of a second than our Sun will emit over 100,000 years. This energy erupts in colossal flares of gamma rays and X-rays, flashes so brilliant they can temporarily outshine every other gamma ray source in the entire observable universe, even from billions of light years away. These are the desperate signals from a captive star twisting in its own magnetic chains. That frantic magnetic energy is dwarfed by another kind of motion, a raw, physical spin that pushes the limits of reality itself. When a pulsar is born from a supernova, it inherits the original star's rotation, but compressed into an object 1,000,000 times smaller. The result is a rotational speed that is almost impossible to comprehend. A newborn pulsar can complete a full rotation in mere milliseconds, spinning hundreds of times every single second. Picture the fastest helicopter rotor you have ever seen, a blur of motion. Now imagine that rotor is the size of a city and spinning thousands of times faster, a cosmic blender churning the fabric of space around it. This dizzying speed is a direct consequence of one of physics' most fundamental rules, the conservation of angular momentum. Just as an ice skater spins faster when they pull their arms in, the collapsing core of the giant star spins faster and faster as it shrinks. All the rotation that was once spread across a star 100 million miles wide is now concentrated into a sphere just 12 miles across. This furious rotation powers the pulsar's most famous feature, its lighthouse beam. The intense magnetic fields of the star funnel radiation into narrow beams that shoot out from its magnetic poles. Because these poles are often misaligned with the star's rotation axis, the beams sweep through space like the beacon of a cosmic lighthouse. From our distant vantage point, we see this as a precise, repeating pulse of light every time a beam sweeps over Earth. That steady, rhythmic blink is the heartbeat of a city-sized corpse spinning at a significant fraction of the speed of light. That furious spin is anchored by a gravity so absolute it dictates the very rules of motion. The surface gravity on a neutron star is not just strong, it is a force of cosmic domination, roughly 100 billion times more powerful than the gravity we experience on Earth. This means a simple object, something as small as a marshmallow, carries catastrophic potential. Picture dropping a marshmallow from a height of just 1 meter above the neutron star's surface. Under the relentless pull of that unimaginable gravity, the marshmallow would accelerate to a significant fraction of the speed of light before it ever touched the ground. Its impact would release energy equivalent to a nuclear bomb, all from a single, fluffy confection. This is the power of neutron star gravity, a force that turns the most mundane actions into events of apocalyptic scale. To even dream of escaping this gravitational prison, an object would need to achieve an equally mind-bending speed. This is known as the escape velocity, the minimum speed required to break free from a body's gravitational pull. For Earth, that speed is a manageable 11 kilometers per second. For a neutron star, the escape velocity is a staggering half the speed of light. Nothing, not even light itself, can escape once it crosses a certain threshold, which is why these objects are such perfect gravitational traps. This is the ultimate expression of their power, a force that bends the paths of photons and dictates the ultimate speed limit for anything trying to flee its surface. Even that impossibly dense sea of neutrons is not the final word on what lies within. The classic image of a neutron star as a simple ball of pure neutrons is a cosmic oversimplification. In reality, these objects are structured, layered cosmic onions with radically different zones of matter, each governed by its own bizarre physics. The outermost layer, the crust, is a crystalline lattice of atomic nuclei, predominantly iron, so compressed that it forms the universe's strongest known material. But dive just a few meters down and you leave all conventional matter behind. Here, in the inner crust and mantle, the pressure becomes so overwhelming that atomic nuclei dissolve into that famous sea of neutrons. Yet even this sea is not placid. It is a superfluid, a frictionless quantum liquid that can flow without any loss of energy forever. This alone would be strange enough, but the true mystery lies at the very heart of the star. In the core, the pressure reaches its ultimate extreme, crushing matter to densities that may exceed even that of an atomic nucleus. Under these unthinkable conditions, the neutrons themselves may not survive. They could shatter, breaking down into their most fundamental components, quarks. This could create a soup of free quarks, a state of matter called quark-gluon plasma, or even stranger particles known as hyperons. Some theories suggest the core might become a single, gigantic lump of strange matter, a stable form of matter made of up, down, and strange quarks. This makes every distant neutron star we observe a direct experiment. We cannot possibly build a machine on Earth that can recreate the pressures inside their cores. So, by studying their spin, their cooling rates, and the gravitational waves they emit, we are essentially reading the results of nature's most extreme physics experiment. Each faint signal is a data point helping us answer one of the most profound questions: what happens to matter when you crush it beyond any recognizable form? This cosmic experiment at the heart of a neutron star has consequences that reach all the way to your finger. The very elements that make up our world, including the gold in a wedding ring or the uranium that powers reactors, were born in the most violent events the universe can produce. The secret to their creation is a frantic, chaotic process called rapid neutron capture, or the R process. For an atomic nucleus to become a heavy element like gold or platinum, it must be bombarded by an immense flood of free neutrons in an incredibly short amount of time. This is not a gentle, slow build. It is a frantic, all-you-can-eat buffet for atomic nuclei, forcing them to gulp down neutrons before they have a chance to decay. This rare and extreme environment exists in only a few places, and one of the most prolific is the aftermath of a neutron star merger. When two of these ultra-dense corpses spiral together and collide, they do not simply create a bigger star. The cataclysm shreds them, ejecting clouds of their neutron-rich material into space at incredible speeds. Inside these hot, expanding clouds, the conditions are perfect. Atomic nuclei are bathed in an overwhelming sea of free neutrons, allowing them to rapidly climb the periodic table, forging elements far heavier than iron in an instant. This stellar alchemy is so efficient that a single merger can create gold, platinum, and other rare elements with a combined mass many times that of our entire planet. So the next time you hold a piece of gold, consider its origin. You are holding a relic from a cosmic collision that happened billions of years ago, a direct product of two dead stars meeting in a final, glittering embrace. This glittering aftermath of a stellar death begins with a final, desperate struggle deep inside a giant star. For millions of years, the star has been a cosmic battleground, its immense gravity constantly trying to crush it inward, held at bay only by the intense pressure from nuclear fusion in its core. But every fuel source eventually runs out. When the star finally exhausts its last reserves of iron, the battle is lost in an instant. With no fusion left to push back, gravity wins the war. The star's core, a sphere of iron roughly the size of Earth, no longer has the strength to support its own weight. It collapses catastrophically, falling inward at a quarter of the speed of light. In less than 1 second, this entire core is crushed from a size larger than our planet down to a city, becoming a proto-neutron star of unimaginable density. The collapse halts so abruptly that it sends a titanic rebound shockwave screaming back outward. This wave slams into the infalling outer layers of the star with the force of a septillion nuclear bombs, blasting them into the surrounding void in one of the most energetic events since the Big Bang itself. We call this a core collapse supernova, and for a brief time it can outshine an entire galaxy. What remains in the heart of that expanding cloud of stellar debris is the collapsed core. Its ultimate fate is a cosmic balancing act. If the leftover core weighs between 1.4 and 2.5 times the mass of our Sun, the inward crush of gravity is perfectly matched by a quantum mechanical force called neutron degeneracy pressure. The collapse stops and a stable neutron star is born, a cosmic phoenix forged in the heart of a stellar inferno. This is the violent origin story of every single neutron star we observe, a testament to the universe's power to create from utter destruction. That critical balance between gravity and quantum pressure is defined by a cosmic boundary line. For a star's collapsed core to become a neutron star, its mass must fall within a very specific window. The lower boundary is known as the Chandra limit, named for the brilliant astrophysicist who first calculated it. This limit, approximately 1.4 times the mass of our Sun, is the absolute maximum mass a white dwarf star can support. A white dwarf is a simpler kind of stellar corpse, a dense Earth-sized sphere held up by the pressure of its own electrons, a force called electron degeneracy pressure. If a white dwarf gains even a little more mass, pushing it over this 1.4 solar mass threshold, that electron pressure catastrophically fails. The star can no longer resist its own weight, and it collapses further, triggering a supernova and leaving behind a neutron star. But this new object, the neutron star, has its own ultimate limit. This upper boundary is the Tolman-Oppenheimer-Volkoff limit, often called the TOV limit. This is the absolute maximum mass that even the incredible pressure of a sea of neutrons can withstand. While the exact number is still a subject of intense research, it is theorized to lie somewhere between 2 and 3 times the mass of our Sun. Every single neutron star we observe, no matter how distant, is a test of this cosmic rule. Its very existence tells us its mass is below this ultimate threshold. But what happens to a neutron star that dares to cross this final line? Imagine a neutron star in a binary system, slowly siphoning material from its companion. With each bite of stolen gas, it grows heavier. If its mass eventually creeps past the TOV limit, the neutron degeneracy pressure that has held it up for millions of years suddenly and completely vanishes. In an instant, there is nothing left to fight gravity. The star's own weight becomes its executioner, and it undergoes total gravitational collapse. The city-sized sphere of nuclear pasta and superfluid is crushed into an infinitely small point, vanishing from the observable universe and leaving behind only its gravity, a black hole. This is why studying the masses of the most distant neutron stars is so crucial. Each measurement helps us pinpoint this final boundary, the exact mass where matter itself surrenders and disappears forever. That steady, rhythmic heartbeat from a spinning stellar corpse is more than just a cosmic curiosity. It is one of the most precise time-keeping mechanisms in the universe. The regularity of a pulsar's blink can surpass the accuracy of atomic clocks here on Earth, turning these distant objects into nature's own perfect metronomes. This incredible precision opens up a universe of practical and profound applications, starting with a direct test of Einstein's grand theory of gravity, general relativity. When a pulsar is locked in a tight orbit with another dense object, like another neutron star or a white dwarf, the system becomes a perfect natural laboratory. The intense gravity warps spacetime itself, causing tiny, measurable shifts in the timing of the pulsar's pulses. By tracking these minuscule delays and advances with exquisite care, astronomers have confirmed predictions of general relativity with a level of accuracy Einstein himself could only have dreamed of. Each perfectly timed pulse is a data point in the most extreme physics experiment imaginable, proving that space and time are indeed curved by mass and energy. This precise timing also paints a vision of a future cosmic GPS. Just as sailors once used lighthouses to navigate treacherous coastlines, a network of pulsars could one day guide spacecraft between the stars. By comparing the arrival times of pulses from several known pulsars, a ship traveling in the deep dark could triangulate its position anywhere in the galaxy with phenomenal accuracy. The faintest, most distant pulsars are the ultimate challenge for this idea. Their signals are whispers from the edge of everything, stretched and weakened by their epic journey across the expanding cosmos. Detecting them at all is a monumental feat of engineering, a testament to how far our technology has come, and a hint at the navigational charts future explorers might one day use to sail the starry ocean. These distant pulses even help us listen for the faintest ripples in reality. Vast networks of telescopes on Earth are tuned to arrays of millisecond pulsars, the fastest spinning and most stable of them all. The idea is to use them as a galaxy-sized gravitational wave detector. A passing gravitational wave, born from the collision of supermassive black holes, would minutely stretch and compress the space between us and the pulsars. This would cause the pulses to arrive a fraction of a second early or late in a specific, correlated pattern across the sky. By monitoring this cosmic choir of pulsar ticks, we are building an ear capable of hearing the low-frequency hum of the universe itself, a background rumble from the most colossal events in existence. Even the universe's most perfect clocks can sometimes skip a beat. Every so often, a pulsar that has ticked with metronomic precision for years will suddenly, inexplicably, speed up its spin in a fraction of a second. Astronomers call these events glitches, and for a brief moment, the steady cosmic heartbeat stutters. The cause of this strange behavior lies deep within the star's layered interior, a place where two different worlds of matter collide. The solid crust, that crystalline lattice of iron, is locked in a rigid, slow spin, but beneath it, the superfluid core of neutrons spins completely freely, a frictionless quantum liquid that feels no drag. Over time, this superfluid interior can actually spin faster than the crust that contains it. Then, something gives way. Perhaps a microscopic piece of the crust, a mountain of nuclear pasta, fractures in a starquake. This sudden shift unlocks the superfluid, allowing its stored rotational energy to transfer instantly to the entire star. It is like stirring a cup of coffee with a spoon and then having the liquid inside suddenly whip the spoon around faster. The entire star experiences a tiny but measurable speed bump in its rotation. For scientists, these glitches are not malfunctions, they are golden opportunities. Each one is a fleeting window into the neutron star's hidden heart, offering clues about the strange states of matter locked inside. By analyzing how a glitch happens and how the star recovers, we can probe the properties of that mysterious superfluid and the strength of the crust that binds it. Every distant pulsar glitch we observe adds another piece to the puzzle of what a neutron star truly is, not just a simple ball, but a complex and dynamic cosmic engine. The steady tick of a pulsar can be shattered by a far grander cosmic event, the final dance of two stellar corpses. This is the neutron star merger, a cataclysm where two of these ultra-dense objects, locked in a gravitational embrace, slowly spiral inward over millions of years. As they draw closer, their immense masses whip space-time around them into a frenzy, sending out ripples known as gravitational waves. These are not waves of light or sound, but literal stretches and squeezes in the fabric of the cosmos itself. For most of the process, these ripples are too faint to notice, but in the last few seconds, as the stars whip around each other thousands of times a second, the waves become a deafening cosmic shout. This is the signal that observatories like LIGO and Virgo on Earth are built to catch. They're incredibly sensitive instruments, using lasers traveling down miles-long tunnels, can detect a change in length smaller than a single proton, allowing us to hear the universe ring like a bell. The collision itself is almost too violent to comprehend. When the two neutron stars finally meet, they do not simply merge into a calm, larger sphere. They rip each other apart in a spectacular flash known as a kilonova. The impact blasts a tiny fraction of their neutron-rich material out into space at incredible speeds, creating a hot, expanding cloud. This is the ultimate cosmic forge. Inside that cloud, atomic nuclei are bombarded by a blizzard of free neutrons, frantically glomming on to create the heaviest elements in the universe through the R process. In a single event, a neutron star merger can forge hundreds of Earth masses of gold, platinum, and uranium, seeding future galaxies with the building blocks for planets and life. The fury does not end there. The merger often births a brief, intensely powerful flash of gamma rays, a short gamma ray burst. For a few seconds, this burst can outshine every other gamma ray source in the sky. A final, defiant scream of energy marking the death of two stars and the creation of entirely new worlds. Even the surface of a neutron star, a place of unimaginable density, can be cloaked in a fleeting shroud. Some of these cosmic corpses possess atmospheres, though the word barely applies in any earthly sense. This is not a blanket of air, but a ghostly veil, possibly just a few centimeters thick and composed of elements like hydrogen or carbon. Yet, despite its negligible depth, this atmosphere is a place of staggering violence, heated to temperatures of millions of degrees by the star's furious energy. For astronomers, this superheated shroud is a gift, a luminous fingerprint that reveals secrets we could never otherwise perceive. As this intense heat radiates away, it does so primarily as X-rays. By meticulously dissecting the spectrum of these X-rays, splitting them into their constituent energies like a prism, scientists can read the atmosphere's story. The precise pattern of light and shadow in the spectrum tells them the star's surface temperature with incredible accuracy. It reveals the crushing strength of its surface gravity, and it can even provide a measurement of the star's radius. This is a profound measurement, knowing the size of an object with the mass of a sun, but the diameter of a city is a direct test of our theories about the state of matter at these extremes. The thin, hot breath of a neutron star's atmosphere is in effect a precise diagnostic tool, allowing us to probe the very nature of the bizarre quantum material that lies beneath. That rigid crust, the universe's strongest material, is not perfectly smooth. It is scarred by what we call mountains. On Earth, mountains are colossal features, towering kilometers high, pushed up by the slow, grinding force of tectonic plates. On a neutron star, a mountain is a microscopic imperfection, a bump that might rise a mere few centimeters from an otherwise flawless surface. This minuscule height is the absolute maximum the star's ferocious gravity will allow. Anything taller would simply collapse under its own weight, flattened into the superfluid sea below. Yet these tiny features are anything but insignificant. Their very existence is a testament to the incredible strength of the neutron star's crust, that nuclear poster lattice, which is strong enough to support these minuscule mountains against a gravitational pull 100 billion times Earth. To hold that image, picture the entire Himalayas compressed down to the height of a single coin. That is the scale of deformation we are talking about on the surface of a cosmic zombie. But these are not static features. As the neutron star spins, these tiny mountains do not simply rotate with it. They create a wobble in the fabric of space-time itself. Imagine a perfectly smooth sphere spinning in water. It would create little disturbance, but the moment you glue a single grain of sand to its surface, that grain would churn the water with every rotation. On a cosmic scale, a neutron star's mountains do the same thing to space-time. Their immense mass, concentrated in such a tiny bump, whips through the cosmos as the star spins, generating a constant, faint tremor in reality. These are continuous gravitational waves, a permanent ripple flowing outward from the star. Our most advanced observatories, like LIGO and Virgo, are now listening intently for this specific, quiet hum amidst the violent crashes of black hole mergers. Detecting it would open an entirely new window into the physics of these distant objects, allowing us to map the topography of a city-sized sphere from thousands of light years away. That microscopic mountain range sits atop a furnace of almost mythical intensity. The surface of a neutron star, while still searing at 1,000,000 degrees, is merely the cooled outer skin of a far hotter interior. Deep within its heart, temperatures can initially soar to billions of degrees Celsius, a heat born directly from its violent birth. This is not a lingering warmth from the original star's fusion. That fire was extinguished in the supernova. Instead, this phenomenal heat is the trapped energy of the collapse itself. When the star's core imploded, an immense amount of gravitational energy was released in an instant, converted into a storm of neutrinos and heat that became locked inside the newly formed neutron star. The star's incredible density acts as a perfect insulator, preventing this heat from escaping easily. It is like a thermos bottle forged on a cosmic scale, keeping a sip of the Big Bang's fury warm for millions of years. This internal furnace is not just a leftover relic, it is the active engine that powers the star's most bizarre behaviors. The phenomenal heat is essential for maintaining the superfluid state of the neutron sea in the core. Without that immense thermal energy agitating the particles, the frictionless quantum liquid could not exist. It is this combination of unimaginable heat and density that allows the neutron star's interior to behave as a single, coherent superfluid, a state of matter that fundamentally shapes how the star spins, cools, and even glitches. The faint X-rays we detect from its surface are the last whispers of that inner inferno, a billion-year-old echo of the star's catastrophic death throes. The crushing magnetic prison of a magnetar builds up unimaginable stress, and eventually something has to break. The star's own crust, that incredibly strong lattice of nuclear poster, cannot withstand the strain forever. It buckles and fractures in a starquake, an event that makes the most powerful earthquakes on Earth seem like gentle tremors. When the crust shatters, it releases all the pent-up magnetic energy in a single, catastrophic flash. We call this a giant flare, and it is one of the most violent outbursts known in the universe. The sheer scale of this energy release is almost beyond belief. In December 2004, a magnetar named SGR 180620, located about 50,000 light-years away within our own Milky Way galaxy, experienced such a quake. For just 1/10 of a second, it unleashed a flash of gamma rays so intense that it measurably ionized the upper layers of Earth's atmosphere, even from that vast distance. That momentary burst contained more energy than our sun will radiate across all wavelengths over the next 100,000 years. It temporarily saturated every gamma-ray detector in space, overwhelming our instruments and becoming, for a fleeting instant, the brightest gamma-ray source ever seen outside of our solar system. To detect a similar flare from a magnetar in a distant galaxy, from the cosmic dawn itself, would be a monumental achievement. It would require an incredible alignment of chance and technology, a perfect cosmic storm where a magnetar in the early universe cracks under its own magnetic pressure at the very moment our telescopes are looking in its direction. Such a detection would be like finding a cosmic fossil that is still screaming. Even the most desolate stellar corpse can become the center of a solar system. The first planets ever discovered beyond our own sun were not found orbiting a warm, life-giving star like our own, but a dead, spinning pulsar. In 1992, astronomers detected tiny, rhythmic anomalies in the clockwork pulse of a neutron star known as pulsar B1257+12. The pulses were arriving slightly early, then slightly late in a repeating pattern. The only possible explanation was that the pulsar was being gently tugged back and forth by the gravity of at least two small, orbiting worlds. This was a monumental discovery, proving that planets could form and persist in the aftermath of stellar Armageddon. The very first exoplanets we knew of were pulsar planets, survivors of the most violent environment imaginable. So how do planets form around a cosmic zombie? The leading theory points to a destructive genesis. The pulsar likely had a companion star, a binary partner. When that partner star went supernova, it could have been torn apart, or the pulsar's own supernova may have catastrophically disrupted its neighbor. Either way, the result was a vast disk of debris, a cloud of pulverized stellar materials swirling around the newborn neutron star. From this wreckage, this cosmic graveyard dust, gravity began to pull matter together anew, forging a second generation of planets. These are not worlds born from the gentle collapse of a primordial cloud, but from the ashes of a stellar catastrophe. Any planet orbiting a pulsar is subjected to a constant, sterilizing barrage. It is bathed in the pulsar's relentless beams of X-rays and gamma rays, a downpour of high-energy radiation that would instantly strip away any atmosphere and scorch the surface to a crisp. These are not worlds where life could ever take hold, yet their existence is a profound testament to the resilience of matter and the universality of physical laws. Even in the hostile, post-apocalyptic landscape surrounding a stellar corpse, gravity still works to build new worlds, proving that the impulse to form planets is a fundamental force woven into the fabric of the cosmos itself. That furious spin which powers the cosmic lighthouse is not infinite. There exists an ultimate speed limit, a point where the star's own rotation would tear it apart. The force fighting gravity in this cosmic duel is centrifugal force, the same outward push you feel on a spinning amusement park ride. If a pulsar spins too fast, this outward force would overwhelm the immense gravity holding the star together, literally flinging its outer layers into space. Calculations point to this breaking point at around 1,500 rotations every single second. Yet nature, it seems, is cautious. The fastest pulsar we have ever found, known as pulsar J17482446 AD, spins at 716 times per second. It is incredibly fast, a blur completing more than 43,000 full rotations every minute, but it is still only halfway to that catastrophic theoretical edge. This gap between the fastest we see and the fastest that is possible is a profound mystery. What is stopping them? The answer lies in the delicate balance of forces within the star's bizarre interior. The precise point of rupture depends entirely on the star's internal structure, the stiffness of that nuclear pasta crust, and the nature of the superfluid core. Finding a pulsar spinning even closer to 1,500 Hz, especially one from the distant, early universe, would be a revolutionary discovery. It would act as a natural stress test, pushing our models of ultra-dense matter to their absolute limit. The star's maximum spin is a direct report on the strength and composition of its quantum heart, a single number that reveals everything about what holds a cosmic zombie together against its own desperate need to fly apart. This steady cosmic heartbeat offers more than just perfect timing. It provides a ruler for the universe itself. Certain pulsars, especially the older, recycled millisecond pulsars, spin with such metronomic stability that they function as cosmic lighthouses of known brightness. Astronomers call these objects standard candles, and they are one of our most powerful tools for measuring the vast emptiness between galaxies. The principle is elegant in its simplicity. Just as a distant lighthouse bulb has a known intrinsic brightness, allowing a sailor to judge its distance by how dim it appears, a standard candle pulsar has a predictable, steady pulse. But astronomers do not just measure the dimness of its light. They use the pulse's arrival time with even greater precision. As the pulsar's signal travels across the expanding universe, its journey is stretched by the fabric of space itself. This stretching causes a minute, measurable delay in the rhythm of the pulses over immense distances. By analyzing this subtle slowdown in the heartbeat, scientists can calculate the pulsar's distance with phenomenal accuracy. This method allows us to triangulate positions across billions of light years, using the pulsar's own predictable rhythm as a fixed reference point in a shifting cosmos. These distant, ticking clocks are helping to build a three-dimensional map of the universe's large-scale structure, revealing the great cosmic web of galaxies and voids. More profoundly, by comparing distances measured with these pulsars to their redshifts, we can trace the history of the universe's expansion. Each stable pulse from the cosmic dark is a data point in the grandest experiment of all, helping us understand how the stretching of space has changed over billions of years and what mysterious force is driving it ever faster. The steady tick of a pulsar is a predictable rhythm, but the cosmos sometimes screams without warning. Across the gulf of space, telescopes occasionally catch a burst of radio energy so powerful it dwarfs entire galaxies, yet it lasts for less than the blink of an eye. These are fast radio bursts, or FRB, and they represent one of the most tantalizing puzzles in modern astronomy. For a few milliseconds, a single point in the sky erupts with more energy than our sun emits in 80 years, and then it vanishes. The source of these colossal, fleeting shouts was a complete mystery for years, with theories ranging from colliding black holes to alien engineering. But the evidence is now pointing towards a familiar yet extreme culprit. The leading suspects are magnetars, those same magnetic monsters whose starquakes produce devastating gamma-ray flares. A magnetar in the grip of an immense crustal fracture could unleash a titanic shudder through its magnetic field, a convulsion that would accelerate particles to near light speed, generating a brilliant, coherent flash of radio waves visible across the universe. This theory gained incredible weight when a magnetar within our own galaxy was caught in the act, producing a radio burst that, while weaker than the extragalactic signals, had all the same telltale characteristics. The most profound clues come from the repeating FRBs. Unlike one-off bursts, these sources flash again and again from the same patch of sky. By tracing these repeating signals back to their home galaxies, astronomers have found they originate in incredibly distant, often turbulent stellar nurseries, the very environments where young, highly magnetized neutron stars are expected to form. It seems the universe's ultimate cosmic zombies are not just whispering to us with their steady pulses, but occasionally they let out a short, desperate scream that echoes for billions of years. A pulsar and a magnetar might seem like siblings, but their differences are as stark as a campfire compared to a supernova. Think of every pulsar as a cosmic lighthouse, its steady beam powered by its furious rotation. Its primary energy source is the slow, gradual loss of its own spin. A magnetar, however, is a different kind of monster entirely. It is a magnetic prison, a star whose incredible power comes not from spinning quickly, but from the slow, agonizing decay of the most powerful magnetic fields in the universe. This magnetic dominance dictates everything. While a typical pulsar can spin hundreds of times per second, a magnetar's rotation is often sluggish, completing a turn only once every 2 to 10 seconds. Its magnetic field is so overwhelmingly strong that it acts as a cosmic brake, rapidly slowing the star's spin soon after its birth. all that pent-up magnetic energy has to go somewhere, and it leaks out in a constant, seething torrent of high-energy X-rays and occasional planet-sterilizing gamma-ray flares. This is the fundamental distinction. You observe a pulsar for its perfect, predictable rhythm. You watch a magnetar for its violent, unpredictable temper. Yet the line between them is not always permanent. Some neutron stars are known to switch states. A magnetar, after a few tumultuous millennia of expending its magnetic fury, may calm down and begin behaving more like a conventional, rotation-powered pulsar. Conversely, some pulsars might reveal hidden, magnetar-like outbursts, suggesting a reservoir of magnetic power lurking beneath a calm exterior. This blurring of categories tells us that these cosmic zombies are not just static relics. They are dynamic, evolving objects, and their classification often depends on which of their two immense powers, spin or magnetism, is currently screaming the loudest into the void. This cosmic zombie's gravity is so potent it twists the very stage upon which light performs. A neutron star's immense mass warps the fabric of spacetime around it, creating a deep, invisible well as predicted by Einstein's theory of general relativity. This curvature is not just a theoretical idea, it has a direct and observable consequence called gravitational lensing. Think of spacetime as a taut, stretched rubber sheet. Placing a massive object like a neutron star onto this sheet causes it to sag, creating a deep dimple. Now, imagine a beam of light from a distant star traveling across this warped sheet. The light does not travel in a straight line as we expect. Instead, it follows the curve of the dimple, its path bending around the dense object. From our vantage point, this makes the background star appear to shift from its true position, or it can even be magnified and distorted into multiple images, like a funhouse mirror made of pure gravity. This effect transforms the neutron star into a natural, cosmic telescope. If we could perfectly align a distant galaxy, a neutron star, and our telescopes, the star's gravity would act as a lens, amplifying the faint light from the galaxy behind it. This would allow us to see details in that galaxy that would otherwise be forever invisible to us. But the lensing works both ways. By meticulously measuring how much the neutron star bends the light of a background object, astronomers could perform the ultimate way-in. They could calculate the star's mass and even map the distribution of that mass within its city-sized diameter with unprecedented precision. This is an incredibly difficult observation, requiring perfect cosmic alignment and instruments of phenomenal sensitivity. Yet for future observatories, it represents a tantalizing prospect, a way to use the universe's own distortions to uncover the deepest secrets of its most dense objects. Even the universe's ultimate zombies face a final destiny. Across trillions of years, a lone neutron star embarks on an epic journey of cooling. The searing heat from its violent birth, once measured in billions of degrees, will slowly leak away into the void. With no internal fusion to replenish its energy, the star's inner furnace will gradually dim. As it cools past a critical point, the chaotic dance of its atomic nuclei will slow and finally lock into a rigid, ordered structure. The entire star, a city-sized sphere of ultra-dense matter, may transform into a single, perfect crystal. It would become a cold, dark diamond drifting through the emptiness of a dying universe, a monument to a star that was, its light and spin long since faded into absolute zero and silence. This is the peaceful, if desolate, end for a solitary stellar corpse, but not all neutron stars are alone. Many are locked in binary systems, and for them, the future holds a far more dramatic finale. A neutron star with a stellar companion is a patient predator. Its immense gravity can slowly siphon gas from its partner over billions of years. With each mouthful of stolen matter, the neutron star grows heavier, inching closer to that ultimate boundary, the Tolman-Oppenheimer-Volkoff limit. If its mass finally tips over that critical edge, the delicate balance that has sustained it for eons shatters in an instant. the neutron degeneracy pressure that has valiantly fought gravity since its birth suddenly and completely vanishes. Nothing remains to hold back the collapse. In less than a heartbeat, the entire structure implodes. The city-sized sphere of nuclear pasta and superfluid is crushed into an infinitely small point. It vanishes from the observable universe, leaving behind only its gravity, a black hole, marked by an event horizon from which not even a final whisper can escape. This is the ultimate choice for these cosmic remnants: to fade slowly into a crystalline ghost or to cross the final threshold and become nothing at all. That cosmic collision we have been exploring has a direct soundtrack to the creation of gold. In the vacuum of space, no sound travels as we know it, but the merger of two neutron stars makes the universe itself ring like a bell. When the LIGO Observatory detected the gravitational waves from such an event, the data was not just lines on a graph. Scientists translated the ripples in space-time into a frequency our ears can hear. The result is a brief, rising cosmic chirp. It begins as a low hum and rapidly sweeps upward in pitch before cutting off abruptly. This is not a sound traveling through air, but the literal vibration of reality itself, a direct audio recording of space-time being stretched and squeezed by the final, frantic orbits of two stellar corpses. That chirp is the sound of their death spiral, the moment of their cataclysmic impact, and the birth of the kilonova that forges the universe's heavy elements. To hear it is to listen to the universe's most powerful alchemy in action, a fleeting whisper that tells a story of destruction, creation, and the very origins of the matter that makes up our world. This patient theft of matter is a one-sided cosmic dance. In a binary system, a neutron star and its companion star are locked in a mutual orbit. But if the two stars are close enough, the neutron star's overwhelming gravitational pull reaches out and begins to strip the outer layers of its stellar partner. This stolen gas does not fall directly onto the neutron star. Instead, it forms a vast, swirling whirlpool of superheated material called an accretion disk. Picture water spiraling down a drain, but on a stellar scale and moving at nearly the speed of light. As the gas particles in this disk rub against each other, friction raises their temperature to staggering extremes, heating them to millions of degrees. At such blistering temperatures, the disk does not glow with visible light. It erupts in a torrent of high-energy X-rays, shining with the power of 10 suns. We call these systems X-ray binaries, and they act as brilliant beacons in the high-energy sky. Their intense X-ray output makes them visible across colossal intergalactic distances, allowing our space telescopes to pick out the feeding frenzy of a single cosmic zombie, even from the farthest reaches of the observable universe. This process of accretion does more than just create a bright light show. The gas piling onto the neutron star's surface carries with it immense energy and, crucially, angular momentum. This constant stream of infalling matter can actually spin the neutron star up, accelerating its rotation over thousands of years. This is how a slow, old pulsar can be recycled into a millisecond pulsar, a cosmic clock spinning hundreds of times per second, all because it spent eons siphoning life from its neighbor. The companion star, meanwhile, is slowly consumed, its mass relentlessly devoured by the patient, insatiable gravity of the dead star it orbits. This transformation from a slow cosmic tick to a rapid-fire metronome is one of the universe's most elegant acts of recycling. An old, solitary pulsar, having spun down over millions of years, can be given a second life and a new, breathtaking speed. The secret lies in its relationship with a neighboring star. When the two are close enough, the neutron star's gravity begins to pull a steady stream of gas from its companion. This material does not fall straight down. Instead, it forms a vast, swirling whirlpool of superheated plasma called an accretion disk, orbiting the dead star at nearly the speed of light. As this stolen matter spirals inward, it carries with it a tremendous amount of angular momentum, the same property that keeps a spinning ice skater turning. When this gas finally crashes onto the neutron star's surface, it delivers a constant, gentle push, like a hand spinning a giant cosmic top. Over thousands of years, this relentless feeding can accelerate the pulsar's rotation from a lazy turn every few seconds to a frantic blur of hundreds of rotations every single second. The old pulsar is reborn as a millisecond pulsar, a cosmic clock of phenomenal precision. Their stability is so profound that the timing of their pulses is more reliable than the most advanced atomic clocks we can build on Earth. This makes them perfect for one of astronomy's most ambitious experiments, the Pulsar Timing Array. By monitoring a network of these recycled pulsars across our galaxy, scientists use them as a galaxy-sized gravitational wave detector. The subtle, correlated shifts in their arrival times could reveal the low-frequency hum of colliding supermassive black holes, a background rumble from the most colossal events in the cosmos, all heard through the perfectly retuned ticks of a once-dead star. These cosmic zombies obey a bizarre rule of cosmic proportion. While their masses can vary dramatically from 1.1 to 2.3 times the mass of our Sun, their physical size remains almost exactly the same. Every neutron star we know of is crammed into a sphere just 10 to 15 kilometers across. Think about that for a moment. You could have two neutron stars side by side, where one contains twice the mass of the other, yet they would both be the same size. This completely defies our everyday experience. If you were to take two balls of clay of equal size and then add more clay to one of them, you would expect it to grow larger. But inside a neutron star, gravity is so overwhelmingly powerful that adding more mass does not make it expand. It simply crushes the material inside to an even greater density. The extra weight forces the existing matter to pack itself more tightly, like stuffing more and more people into a phone booth without the booth ever getting bigger. This strange behavior makes measuring a neutron star's radius one of the most important goals in all of astrophysics. That single number, the precise size of a city-sized object billions of light years away, is the key to unlocking the true nature of matter itself. It would reveal the equation of state for ultra-dense matter, a fundamental physical law that describes how matter pushes back when you try to crush it beyond all reason. Finding that number would tell us whether the core is a soup of free quarks, a crystal of strange matter, or something even more exotic. Every distant neutron star we observe is therefore a natural laboratory, its unchanging size a direct report on the absolute limits of physical reality. That perfect, unchanging size of a neutron star hides a radical possibility. What if some of these objects are not made of neutrons at all? One of the most exotic theories in astrophysics suggests that the densest neutron stars might actually be something else entirely, strange stars. These would be objects even more bizarre than their neutron star cousins, composed almost entirely of a soup of fundamental particles called quarks. In a normal neutron star, gravity crushes atoms into a sea of neutrons, but the neutrons themselves remain intact. In a strange star, the pressure at the core is so unimaginably high that it breaks the neutrons apart into their constituent quarks. This would create a new state of matter, a perfect fluid of up, down, and strange quarks, the three lightest varieties. This strange matter could be the most stable form of matter in the entire universe. If this hypothesis is true, the implications are staggering. A strange star would be even denser than a neutron star, packing more mass into the same tiny volume. Its surface would not be a solid crust of iron, but a perfect, bare quark surface. This boundary, only a few femtometers thick, would be the smoothest surface in existence, reflecting light with the perfection of a flawless cosmic mirror. How could we ever tell the difference between a distant neutron star and a strange star from billions of light years away? The evidence lies in subtle clues. A strange quark star would cool much faster than a neutron star, as its interior could radiate away heat more efficiently through neutrino emission. We would also look for how it responds to extreme stresses, like the accretion of matter from a companion star. A strange star's quark surface would behave differently during such events, potentially producing a distinct X-ray signature. Every faint pulse and every flicker of X-ray light from these distant cosmic zombies is a potential test for this theory, a search for an object so alien that it is made from the primordial soup of creation itself. The bizarre matter inside a neutron star pushes the strong nuclear force to its absolute limit. This fundamental force is the glue of the universe, the powerful attraction that binds protons and neutrons together inside an atom's nucleus, overcoming the immense repulsion between positively charged protons. In our everyday world, and even in particle colliders, we can only study this force over tiny distances inside a single atomic nucleus. But inside a neutron star, matter is compressed to densities where atomic nuclei are smashed together, shoulder to shoulder, creating a continuous ocean of nuclear material. This is a state of matter that does not exist anywhere else, a single, giant nucleus with the mass of a star. The strong force is no longer just acting between close neighbors, it is governing the behavior of an entire city-sized object. The way this nuclear glue responds to such unbelievable pressure determines everything about the star. It dictates how stiff or soft the ultra-dense matter is, which in turn sets the star's maximum possible mass and its exact radius. When two neutron stars spiral together in a final dance, their immense gravity does not just pull on each other, it stretches them. This tidal deformation, the way each star bulges toward the other just before collision, is a direct probe of the strong force's grip. A stiffer material held firm by a powerful nuclear interaction would resist this stretching more than a softer one. By carefully measuring the gravitational waves from such a merger, we can detect these subtle differences in how the stars deform. Each ripple in space-time carries a fingerprint of the nuclear strong force operating under conditions we could never, ever create on Earth. Every distant neutron star we find is therefore a natural laboratory, reporting back on the fundamental laws that hold reality itself together. On August 17, 2017, the universe sent us a message written in the fabric of space-time itself. The twin detectors of LIGO, along with the Virgo Observatory, felt a distinctive ripple, a gravitational wave signal that was not the deep thrum of black holes but a rising, frantic chirp lasting for nearly 100 seconds. This was the sound of two neutron stars locked in a final, deadly dance, spiraling inward over millions of years until they finally collided. The signal, named GW170817, was a clarion call to every major observatory on Earth and in space. For the first time, we had caught the gravitational wave whisper of a cosmic catastrophe, and we knew exactly where in the sky to look. Telescopes of every kind swiveled to a relatively nearby galaxy called NGC 4993. Within hours, they found it, a brand new pinprick of light that was not a supernova, but something entirely new, a kilonova. This was the multi-messenger astronomy event of a generation, a story told in both ripples and light. The kilonova's rapidly fading glow confirmed the wildest predictions. Its specific color and evolution were the unmistakable signature of the rapid neutron capture process, the frantic forging of heavy elements. In that single collision, an amount of gold and platinum many times the mass of our entire Earth was created and blasted out into the cosmos. The event also solved a decades-long mystery, producing a short gamma-ray burst detected just 2 seconds after the merger's peak. This one observation, a single cosmic event witnessed in gravity and light, tied together the origin of the elements, the source of the universe's most powerful explosions, and the final fate of stellar corpses, truly launching a new era of cosmic understanding. That flawless cosmic mirror is a direct creation of its own immense weight. A neutron star's surface is theoretically the smoothest object of its size in the entire universe. While its crust can support those microscopic mountains, The sheer power of gravity ensures that no feature of any real significance can exist for long. Any irregularity more than a few millimeters high would simply collapse under its own weight, flattened into the superfluid sea below. To grasp this perfection, picture a perfect sphere the size of a city. Now imagine the single tallest mountain on its entire surface is no taller than a grain of sand. This is the level of smoothness we are talking about, a polish achieved by a gravitational force 100 billion times stronger than Earth. This incredible smoothness is not just a cosmic curiosity, it is a critical factor for astronomers. When scientists model the star's X-ray emission, the assumption of a nearly perfect surface shapes their predictions. A rougher surface would scatter and distort the high-energy light in a different way. Furthermore, this smoothness is vital in the hunt for continuous gravitational waves. A perfectly smooth, spinning neutron star would be virtually silent in gravitational waves, but those tiny, millimeter-high imperfections are what make it hum. As the star rotates, these minuscule bumps and wrinkles whip through space-time, generating a faint, continuous ripple. The smoother the star, the quieter its gravitational song, and the more challenging it is to detect. So, in seeking that faint tremor, we are essentially measuring the ultimate limits of smoothness, listening for the whisper of a cosmic grain of sand on a perfect sphere billions of light years away. A cosmic predator spins in the dark, slowly devouring its partner. This is the Black Widow pulsar, a millisecond pulsar engaged in a relationship of ultimate destruction. Reborn through accretion, these pulsars spin hundreds of times per second, and their renewed energy comes with a terrifying side effect. They blast their companion star with an unrelenting hurricane of radiation and high-energy particles. This is not a gentle stellar wind, it is a pulsar wind, a gale of fury that strips away the companion's atmosphere, blowing it off into space piece by piece. Imagine a star being slowly sandblasted by a cosmic fire hose, its outer layers torn away and heated into a vast, swirling cloud of plasma. Over millions of years, this relentless assault takes its toll. The companion star, once a sun-like sphere, is whittled down to a tiny, charred remnant, a cinder of its former self. In some of the most extreme cases, the pulsar may completely evaporate its stellar partner, leaving behind nothing but a fast-spinning, solitary pulsar and a faint, expanding cloud of stellar debris. This grim process explains the existence of many lone millisecond pulsars, the silent survivors of a cosmic murder. These Black Widow systems are a stark reminder that in the universe, even the dead can wield immense power, capable of erasing another star from existence with nothing but their own resurrected spin. Pinpointing a city-sized object billions of light-years away feels like an impossible task, yet astronomers have devised ingenious methods to do just that. For the closest pulsars within our own Milky Way, they sometimes use a technique as old as navigation itself, triangulation. By observing the pulsar from opposite sides of Earth's orbit around the Sun, they can detect a tiny apparent shift in its position against the backdrop of more distant stars. This method, called parallax, provides a direct and reliable geometric distance, but it only works for our closest stellar neighbors. For the vast majority of neutron stars, especially those in other galaxies, we need a completely different approach, one that listens to the pulse itself. As a pulsar's signal travels across thousands or millions of light years, it does not journey through a perfect vacuum. It passes through the diffuse fog of the interstellar and intergalactic medium, a sparse soup of free electrons. This cosmic fog has a curious effect on the pulsar's radio beam. It acts like a prism, but instead of separating light into colors, it delays the lower frequency radio waves. The higher frequency part of the pulse arrives at our telescopes just a fraction of a second before the lower frequency part. This delay is called the dispersion measure. The greater the delay, the more electrons the signal has traveled through, which generally corresponds to a greater distance. It is a brilliant concept, using the universe's own static to gauge depth. Yet this method comes with a significant challenge. To turn that delay into a precise distance, you need to know the average density of electrons along the precise path the signal took. Is the path through a dense galactic spiral arm or an empty void between galaxies? Calibrating this electron map for signals coming from beyond the Milky Way is incredibly difficult, making every distance estimate to an extragalactic neutron star a sophisticated puzzle. Each measurement is a best guess, refined by complex models and cross-checked with other methods, a constant reminder that even the most brilliant cosmic signals travel to us through a flawed and murky lens. That desperate scream from a magnetar's starquake is a local event compared to the true titans of cosmic violence. The merger of two neutron stars can trigger the universe's most powerful explosions since its birth, gamma-ray bursts. These are not mere flares, they are apocalyptic detonations that for a few seconds can outshine every star in the observable universe combined. When two neutron stars complete their final, fatal spiral and collide, the cataclysm does more than just forge gold. In the chaotic aftermath, a fraction of the system's immense energy can be focused into two narrow, oppositely directed jets of material and radiation. These jets, moving at nearly the speed of light, are the key to the entire phenomenon. They are like the cosmic equivalent of a laser beam, concentrating a staggering amount of power into a pencil-thin stream. If one of those jets happens to be aimed directly at Earth, our satellites register it as a brilliant, fleeting flash of gamma rays. We call these short gamma-ray bursts, and they typically last for less than 2 seconds, a brief but ferocious final testament to the collision. The energy packed into that short signal is almost beyond comprehension, representing the raw power of two stellar corpses being annihilated and reborn as a black hole. Detecting one of these bursts from a galaxy billions of light years away means we are witnessing a beam of pure energy that has been traveling since the universe was young, a final, focused shout from a cataclysm that shaped the cosmos. That single, unchanging radius for neutron stars of different masses is the ultimate clue to a fundamental cosmic law. This rule is known as the equation of state, and it is the master key that unlocks the true nature of matter inside these stars. Think of it as the universe's own recipe for ultra-dense matter, a precise description of how this bizarre substance pushes back when you try to crush it with unimaginable force. The equation of state defines the relationship between the immense pressure at the star's core and the resulting density of the material. This single relationship dictates everything about the star's observable properties. It determines whether a neutron star is relatively squishy, able to compress significantly under its own weight, or incredibly rigid, resisting further collapse. This inherent stiffness, or lack thereof, is what sets the star's maximum possible mass and its precise radius. Different theoretical models propose wildly different equations of state. One model might predict that the core is a soft soup of free quarks, leading to a more compact, squishy star. Another might insist the interior is a rigid crystal of strange matter, resulting in a larger, stiffer object. We cannot recreate these pressures in any laboratory on Earth, so how do we test which model is correct? We look to the cosmos. Every distant neutron star we observe is a natural experiment. By carefully measuring its mass and radius, we are effectively conducting a stress test on these theoretical models. When we find a neutron star with a large mass and a small radius, it immediately rules out all the equations of state that are too soft to support such a configuration. Conversely, a star with a low mass and a large radius would disprove models that are too rigid. Each new measurement is another piece of data, helping us cross possibilities off the list and zero in on the one true equation that governs matter at its absolute limit. This is not an abstract exercise. Finding this holy grail of physics would tell us definitively what happens when you crush matter beyond the atom, beyond the nucleus, and into a state that should not exist. The universe's densest stellar cities are perfect breeding grounds for cosmic zombies. Far out in the galactic halo, ancient globular clusters drift like spherical swarms, each containing hundreds of thousands of stars packed into a relatively tiny volume of space. In these crowded stellar metropolises, stars are not isolated. They brush past each other, their gravitational fields constantly interacting in a complex dance. This makes globular clusters the ultimate neutron star factories. When a massive star explodes in a supernova within the cluster, the resulting neutron star is often born into a crowded neighborhood. It has a high probability of gravitationally capturing a partner star, stealing a binary companion from the stellar throng. This close proximity is the key to resurrection. The neutron star begins to siphon material from its new partner, a process that over billions of years spins it up into a millisecond pulsar. This is why some of these ancient clusters are known to harbor dozens, sometimes even hundreds, of these rapidly spinning stellar corpses. They are cosmic graveyards that are paradoxically teeming with vibrant, energetic activity, each pulsar a testament to a stellar interaction that happened billions of years ago. These clusters act as perfect natural laboratories, allowing astronomers to study an entire population of neutron stars all at once, all at the same vast distance. By comparing their spins, their masses, and their relationships with companion stars, we can trace the entire life cycle of these objects, from their violent births to their final, high-speed resurrection. That frantic spin and immense magnetic field of a pulsar creates a hurricane of its own. The star continuously flings out a gale of ultra-relativistic particles, a wind of electrons and positrons moving at nearly the speed of light. This is not a gentle breeze, it is a pulsar wind, a storm of matter and antimatter screaming into the void. When this hurricane slams into the slower-moving debris of the original supernova explosion, or even the thin gas of the interstellar medium, the collision is spectacular. The result is a pulsar wind nebula, a glowing, dynamic cloud of light that acts as a cosmic signpost for the hidden engine at its core. The particles in the wind are forced to spiral along the pulsar's magnetic field lines, and as they accelerate, they release energy across the electromagnetic spectrum, from radio waves all the way up to gamma rays. This process makes the nebula shine with an otherworldly, structured light, often appearing as a complex web of filaments and jets. The most iconic example is the Crab Nebula, the expanding remnant of a star whose death was witnessed by astronomers in 1054. At its very center spins the Crab pulsar, a neutron star rotating 30 times every second. Its relentless wind and radiation pour energy into the surrounding cloud, illuminating the entire nebula and powering its eerie, shimmering glow. For astronomers studying the most distant neutron stars, finding a pulsar wind nebula is a major breakthrough. That glowing cloud is a direct and visible confirmation of the pulsar's power, a testament to its ability to energize its environment across billions of light years. By studying the size and brightness of these distant nebulae, we can measure the energy output of the neutron star that drives them, understanding how these cosmic engines influence the galaxies they call home. The bizarre states of matter inside a neutron star are only the beginning of the mystery. These cosmic laboratories push our understanding of physics to its absolute breaking point, forcing us to confront the gaps in our knowledge of reality itself. At the very heart of a neutron star, the density becomes so phenomenally high that the very concept of individual particles begins to dissolve. We are no longer looking at a sea of neutrons, but at a state where the distinction between one particle and the next blurs into a single, unified quantum entity. Our current laws of physics, the twin pillars of general relativity that governs gravity on a large scale and quantum mechanics that rules the subatomic world, fail to describe this extreme environment. They offer contradictory predictions. To truly understand what happens inside a neutron star's core, we need a theory that unites these two great pillars, a single framework known as quantum gravity. This is the holy grail of modern physics, a theory that would describe how gravity works at the scale of individual particles. We cannot build a particle collider powerful enough to recreate these conditions on Earth. But the universe has built them for us. Every distant neutron star we observe is a natural experiment in quantum gravity. Its mass, its radius, and the very way it spins are all direct results of the physical laws operating in its core. By carefully measuring these properties, we are not just studying dead stars. We are testing the fundamental rules that govern all matter and energy in the cosmos, using the universe's most extreme objects to read the fine print of reality. This mysterious gap in the cosmic graveyard holds a profound question about stellar death. Astronomers have mapped the masses of countless compact objects, and a clear pattern emerges, one with a puzzling empty space. We find neutron stars, those dense stellar corpses, with masses up to about 2 times that of our Sun. Then we find black holes, but the lightest of these typically begin at around 5 solar masses. Between 2 and 5 times the mass of the Sun, there is a desert, a place we call the mass gap. Where are all the objects in between? Is this emptiness a fundamental rule of the universe, a sign that the mechanics of a supernova cannot create a remnant in this weight class? Or is it merely a trick of our perception, a detection bias born from the limitations of our current tools? Consider the challenge of finding a lone, dark object in this mass range. A black hole below 5 solar masses would not have the gravitational heft to loudly announce itself through the methods we most commonly use, like the gravitational waves from a merger with another black hole. A neutron star pushed past its normal limits would have collapsed into a black hole, leaving no middle ground. Yet, finding just one object firmly within this gap would send shockwaves through astrophysics. It would force us to rewrite the rules of core collapse supernova, suggesting that stars can die in ways we have not yet imagined, leaving behind remnants that defy our clean categories. The search for this missing link is a hunt for a cosmic rule breaker, an object that could tell us what truly happens when a star runs out of time. These dead stars might be the key to finding the universe's most elusive ghost. Dark matter, the invisible substance that makes up most of the universe's mass, has evaded every direct attempt to catch it. But some scientists propose that neutron stars, with their phenomenal gravity, could be the perfect natural trap. A lone neutron star drifting through the dark matter halo of a galaxy would act like a cosmic vacuum cleaner. Over billions of years, countless hypothetical dark matter particles would be pulled in by its intense gravity, accumulating in its core. There, the particles could collide and annihilate each other, a process that would release energy and gently heat the star from the inside out. This creates a unique and testable prediction. We would expect an ancient, isolated neutron star to have cooled down to near absolute zero after billions of years, its internal furnace long since faded. But if one of these stellar corpses was found to be unexpectedly warm, glowing faintly with a heat that cannot be explained by any other means, it could be the smoking gun. The warmth would be the signature of dark matter annihilating within its heart. This turns every cold, distant neutron star into a potential laboratory. By scanning the skies with infrared and X-ray telescopes, astronomers are essentially taking the temperature of the universe's oldest stellar remnants, searching for the ones that refuse to grow cold. A single, unexpectedly warm neutron star could be the clue that finally illuminates the dark. Even the steady slowdown of a pulsar's spin holds a secret number. Astronomers call this the breaking index, a precise value that should, in a simple universe, be exactly 3. Imagine a spinning top slowing down on a perfectly smooth table, its deceleration following a predictable, elegant rule. That rule, for a pulsar behaving as a pure magnetic dipole, a kind of ideal cosmic lighthouse, gives us that number 3, yet the universe is rarely so simple. When we measure real pulsars, we almost always get a breaking index less than 3. This small discrepancy is a giant clue. It tells us the spin down is not a clean, simple process. Something else is at work, robbing the pulsar of its rotational energy. The culprit could be a fierce particle wind, that relentless hurricane of particles streaming from the star, acting as an extra brake on its spin. Or it might be that the pulsar's mighty magnetic field is itself slowly changing, evolving over millennia and altering the way it taps into the star's rotation. For a distant pulsar, measuring this index is a monumental task. Its signal is a faint whisper, and tracking the minuscule changes in its spin over years from billions of light years away pushes our technology to the absolute limit. But every successful measurement is a triumph. That little number, always shy of 3, is a direct report from the front lines of extreme physics, revealing the intricate and dynamic struggle as a cosmic zombie slowly winds down its furious life. Beneath that unbreakable crust of iron mountains lies a hidden sea. This is not an ocean of water, but a seething, liquid plasma of atomic nuclei and free electrons, superheated to millions of degrees. Imagine a fluid that is also a perfect electrical conductor, a churning, metallic soup held in a state of perpetual, violent motion by the star's immense magnetic field and internal heat. This strange ocean lies directly beneath the solid crust, its surface a sharp and tumultuous interface between two radically different worlds of matter. It is at this boundary where some of the neutron star's most brilliant tantrums are born. For a neutron star feeding on a companion, stolen hydrogen and helium rain down onto its surface, piling up under the crush of gravity. This material sinks through the solid crust, eventually mixing into the superhot plasma ocean below. Here, the conditions become a perfect storm for cosmic violence. The pressure and temperature skyrocket, forcing the accumulated hydrogen to undergo a frantic, runaway fusion. The entire surface layer of the star, over an area the size of a city, ignites in a single thermonuclear flash. In less than a minute, this explosion can release more energy than our sun will emit for an entire week. We see this from Earth as a sudden, brilliant flare of X-rays, a type I X-ray burst that briefly outshines every other source in the sky. These flashes are not the star tearing itself apart, but its surface literally catching fire, a cyclical inferno fueled by the delicate and destructive balance between a rigid crust and a furious liquid heart. Our current maps of the cosmic dead are about to be rewritten by a new generation of observatories. These instruments will transform our whispers of understanding into a clear cosmic chorus, revealing tens of thousands of neutron stars we never knew existed. Leading this charge is the Square Kilometre Array, a radio telescope of almost mythical scale. When its thousands of antennas across 2 continents finally open their electronic ears, it will listen to the sky with such sensitivity that it is expected to discover tens of thousands of new pulsars. This will not just be about quantity. The sheer volume of data will allow us to find the rarest of the rare, the pulsars in the most distant galaxies, the ones spinning at the absolute edge of stability, and the exotic binary systems that push the limits of general relativity. In the high-energy realm, the Athena X-ray Observatory will act as our sharpest eye yet. It will peer into the hearts of distant galaxies and see the faint, hot glow of neutron star surfaces with unprecedented clarity, measuring their size and mass with a precision we can only dream of today. And all the while, the gravitational wave detectors like LIGO, Virgo, and CAGRA will continue to listen. Their upgraded sensitivity will catch the faint ripples from more frequent neutron star mergers, turning those rare cosmic chirps into a regular soundtrack of creation. Together, this fleet of next-generation tools will probe deeper into the universe than ever before, finding neutron stars from the very first epochs of star formation. They will test the equation of state with relentless data, hunt for the missing mass gap objects, and perhaps even catch the first clear signal of a strange star. The silent darkness of space is about to get very, very loud. The rigidity of a neutron star is a number, a single value. We call its love number. This is not a measure of affection, but a precise calculation of how easily its perfect form can be distorted. When a neutron star orbits a close companion, the companion's gravity pulls on it, stretching it into a subtle egg shape. This tidal deformation is a constant, gentle tug of war between the external pull and the star's own immense gravity, which fights to restore its spherical perfection. The love number tells us exactly how much the star yields. A high love number means the star is soft and pliable, deforming significantly under stress. A low number indicates a rigid, stiff object that barely budges. This single value is a direct window into the star's heart because its stiffness is governed entirely by the bizarre state of matter inside. During the final, frantic moments before a neutron-star merger, this deformation becomes extreme. As the two corpses spiral inward, their gravitational fields rip at each other, stretching them into teardrop shapes just before impact. This violent stretching leaves a specific imprint on the gravitational wave signal, a subtle signature woven into the rising cosmic chirp. By extracting the love number from that ripple in space-time, we are essentially performing a remote stress test. We are learning whether the star's core is a soft soup of free quarks that gives easily, or a rigid lattice of nuclear pasta that resists until the very last second. Each merger we detect is not just a crash, it is a laboratory report on the fundamental nature of matter under pressure we cannot create, a direct measurement of the universe's own recipe for its densest objects. Even the name we have given them is a cosmic oversimplification. We call them neutron stars, but this label barely scratches the surface of the bizarre reality within. That name implies a simple ball of pure neutrons, a tidy concept that fits neatly into a textbook. Yet, as we have seen, the interior is a chaotic, layered place where known physics breaks down. The truth is, a neutron star is less a single thing and more a menagerie of exotic particles, a seething zoo of hyperons, pions, and potentially a soup of free quarks. Neutrons are merely the dominant tenant in this quantum apartment building, not the sole resident. The name stuck because it describes the most abundant component we initially understood, but it fails to capture the full spectrum of possibilities. For an object with a core of strange quark matter, the term quark star would be far more precise. If hyperons dominate the heart of the star, then hyperon star would be a better fit. Some scientists even joke about needing a more dynamic name, something that reflects its changing nature like a quantum hybrid object. This is not just semantic nitpicking. The name we use shapes how we think about these cosmic zombies. Calling it simply a neutron star suggests a simplicity that does not exist, potentially blinding us to the wilder, more wonderful truths hiding within. Every new observation, every precise measurement of mass and radius is a test not just of physics, but of our very vocabulary, pushing us to find new words for realities we are only just beginning to perceive. Our cosmic reach for these stellar corpses has a final, unbreakable boundary. We are forever searching for whispers in an expanding storm of silence, and there is a fundamental distance beyond which a neutron star's signal simply vanishes. Its faint pulse of radio waves or X-rays is stretched by the universe's expansion until its frequency is too low for our telescopes to register. The light becomes so redshifted it slips entirely out of the detectable spectrum, fading into the background hum of the cosmos. Even the most brilliant magnetar flare, a shout that could outshine galaxies, becomes an imperceptible sigh after traveling across billions of light years. The most distant neutron stars we have found are already miracles of detection, captured only because a perfect alignment of cosmic chance and human ingenuity allowed their faint signature to rise just above the relentless noise. This horizon of observability is the hard edge of our knowledge, a frontier defined not by our curiosity, but by the immutable laws of physics and the limitations of our own engineering. It is a line drawn in the sand of space-time, separating the cosmic zombies we can study from the infinite legion that remains forever hidden in the dark. This boundary does not mark the end of our quest, however. It is the very reason we build bigger telescopes and more sensitive detectors, constantly pushing our instruments to listen for the next, fainter whisper from the edge of everything. These distant, spinning relics are the universe's final word on stellar life and death. Every neutron star we detect, especially those from the cosmic dawn, is a direct product of a massive star's explosive end, a necessary step in the grand cycle of cosmic evolution. Without these titanic supernovae and the mergers that follow, the cosmos would remain a simple, barren place, filled only with the primordial hydrogen and helium from the Big Bang. These cosmic zombies are the ultimate recyclers. They take the ash of simple stars and, through their violent deaths and collisions, forge the heavier elements that make up our world. The iron in your blood, the calcium in your bones, and the gold in a wedding ring were all blasted into space from such cataclysms billions of years ago. These distant objects are more than just remnants. They are active participants in shaping the universe's chemical future. Their steady pulses and brilliant flares serve as the fundamental beacons that allow us to chart the vast, dark oceans between galaxies. By listening to their rhythms, we can measure the expansion of space itself, tracing the history of how the universe grew from a hot, dense state into the complex, structured cosmos we see today. The most ancient neutron stars are messengers from the era of peak star formation, a time when the universe was a frantic stellar nursery. Their faint signals carry a story of that transformative epoch, a chronicle of how the first generations of stars lived fast, died young, and seeded the void with the ingredients for everything that followed: planets, oceans, and life. To study them is to read the final chapter in a star's biography, a story that ultimately leads back to us. We have traveled to the edge of the observable universe and peered into the heart of a cosmic zombie. From a single teaspoon weighing billions of tons to magnetic fields that could erase a planet's memory from the moon, these distant neutron stars are the ultimate expression of nature's extremes. They are the universe's master alchemists, colliding in spectacular kilinovae to forge the gold and platinum that make up our world. And they serve as perfect natural laboratories, their steady pulses and violent flares testing the laws of physics under pressures we can never recreate. To study the light from these most distant stellar corpses is to read the diary of the cosmos itself, a chronicle written in gravity, spin, and searing radiation that tells the story of how our universe evolved from a simple state into the complex, element-rich place it is today. The next time you gaze up at the night sky, remember that hidden within the vast dark are these incredible powerhouses, spinning silently and shaping the cosmos from billions of light years away. If these cosmic mysteries captured your imagination, help us explore more by liking this video and subscribing for deeper journeys into the universe's greatest secrets. Let us know in the comments which fact about neutron stars astonished you the most.